Hello everyone. Today we will continue the similarity and dissimilarity measures. Actually, today we will study the information-based similarity measures. However, before we get started, let's review the content in the last class first. In the last class, we started from the Mahalanobis distance. The Mahalanobis distance is very similar to the Euclidean distance. However, it considers the shape of the distribution of the data. Actually, it fits its data distribution to the Gaussian distribution, which has the elliptical form, and this and it is also approximated or considered as a right circle, so that it considers the distance at the inside in that circle. For example, here, the example in the last page, shows that, okay, by using the Euclidean distance, the line segment between A and C is longer than the line segment between A and B. So the Euclidean distance between A and C is larger than the Euclidean distance between A and B. Actually, it's twice as long. However, if we consider the Mahalanobis distance, this distribution, the data distribution looks like this like this long. So as we consider it as a circle, then the distance from the center to each end will be considered the same. So if we follow to move this direction, then the distance, but the Mahalanobis distance is shorter than we are actually see, and in this direction, the Mahalanobis distance will be longer than the Euclidean distance as we expected. So here, A and C has moving from A to C follows this line, and moving from A to B follows this line. So by Mahalanobis distance, this distance becomes shortened, and this becomes more longer. So the Mahalanobis distance between A and B is greater than A and C. So that is the main difference between the Euclidean distance and Mahalanobis distance. And we saw the common properties of a distance. This common properties of distance is really important, and we call a distance function which satisfies these properties are metrics or distance metrics, or in short, distance. And also we saw the common property of similarity. The similarity can be considered as the opposite concept of distance or dissimilarity. So it, we can derive the properties of similarity from the properties of the distance in the previous page. And then we saw two similarity measures between the binary vectors. The first one is simple matching coefficient, and the other one is the Jacquard coefficient. For two binary vectors having the same length, there are four cases if we compare each attribute in these vectors. Okay. the first case is f. The first case is 0, 0 case when the attribute values of two vectors are all 0, and the second case is 0, 1, third case is 1, 0, and the last case is 1, 1, of course. So if we count the number of these cases, and we call them our F00, F01, F10, F11. Here F means frequency. And simple matching coefficient counts it simply counts the number of matches. Number of matches here means that the sum of F00 and F11, these are the case of matching. So two attribute values are the same, so we call this case it is matched. However, the case for 0, 1 and 1, 0, we call these cases are dismatched. So here the number of matches over the length of one vector, which is actually n. So this is the simple matching coefficient for the comparison of two binary vectors having the same length. However, for the asymmetric attributes, for example, there are a lot of zeros and only a few ones, like customer transaction data, then this simple matching coefficient can be dominated by the value of f00 because this f00 is a lot larger than f11. Okay. So we used for that case the Jaccard coefficient. The Jaccard coefficient can be calculated ignoring f00 in the simple matching coefficient. So in the numerator, the f00 is ignored and only f11 that we count. And here, even for in denominator, we ignore f00. We just take a sum of f01 and f10 and f1. This is the n minus f00. So for these two vectors, x and y, we saw that x and y are very dissimilar. They are not similar. So we can expect that their similarity may be quite small. However, if we use simple matching coefficient, its similarity becomes 0.7, which is very high because they have common f00 7 times. And they do not have any common f1, any common 1, 1. So by using simple matching coefficients, the similarity between these two vectors, say x and y, will be 0.7. However, if we use Jaccard coefficient, then the numerator of Jaccard coefficient only counts f11, and f11 is 0 in this case. So by using Jaccard coefficient, the similarity between two binary vectors x and y will be 0. Okay. So like this example, if the binary vectors contain a lot of zeros and only a few ones, then the simple matching coefficient and Jaccard coefficient can have very different values. And the next similarity that we saw in the last class was cosine similarity. Sometimes for the vectors, it is more important to the absolute distance of the vectors. I mean that it's quite important, the direction of the vectors, than the absolute values or absolute distance of the vectors. For example, for the text data, which is represented by the term document matrix, the element of each matrix is the number of appearance of a specific word in a specific document. So in this case, the direction of the vector from origin is more important than the distance between the data points, because actually here the example that we made in the last class, if we can see the document A and C, document A contains 2 dogs and 2 animals, and document C is 8 dogs and 8 animals. There, the Euclidean distance is quite large. However, they have same direction from origin. Actually, we can easily expect that they have similar contents, and also maybe this difference can be from the length of text or length of document, because if we can make it see easily from copying A 4 times. Okay, if we copy and paste A 4 times, then that document contains 4 times as many as words frequency than A. So so in this point of view, the document C and A would be very similar. However, the document B, which contains the cat instead of animal, instead of dog, so maybe B is quite different from A and C. Okay. However, if we consider the Euclidean distance, A and B is much similar than A and C, so the Euclidean distance or other distance concept may not be appropriate for this case. So we use cosine similarity, which only considers the directions from the origin for this kind of data. Okay. This cosine similarity is really extensively used in the machine learning society. So please remember the concept and of cosine similarity and when it can be applied. The next one is correlation. Correlation also can be used as one of the similarity measures. So I think you guys already studied the correlation in the probability class or stat class. So I will skip the detailed review for the correlation. The major drawback of correlation is that it only considers the linear relationship between 2 vectors. So if, for example, like example in this page, if 2 vectors have quadratic relationship, the correlation cannot find these patterns. So that it may lead the misunderstanding. for the data. Okay. And here are the characteristics of the three proximity measures according to their behavior under variable transformation. Here we consider two transformations. The first one is scaling. The vectors are scaled by the constant method, or in other words, they are multiplicated by of some constant. And also translation. The any constant vector is added to the original vectors. So the Euclidean distance is not invariant to both scaling and transformation. The result of the Euclidean distance is different if we apply scaling or translation to the vectors. However, the cosine similarity is invariant to scaling because it only considers directions. However, the translation changes the direction or angles from the origin. So the cosine similarity is invariant to scaling, but is not invariant to translation. And for the correlation is both invariant to scaling and translation because in the calculation of correlation, all vectors are normalized. It means that the mean of the vector is subtractive, so it is invariant to the translation, and it is divided by its standard deviation, so it is invariant to the scaling. So the second table in this page is the example of these properties. So we can easily find that the correlation is not changed for both scaling and translation. However, cosine similarity has the different value for when we translate the data points to another point. And for the Euclidean distance, it is we can see that it shows different values both for the cases of the scaling and in translation. So here we saw several proximity measures, actually too many proximity measures. However, they mm, the selection of these proximity measures is highly depending on the domain of application. So if first we need to get the domain knowledge when we actually conduct the data analysis, then we can choose an appropriate proximity measure that can be applied to the domain. Okay. So now today we will start from this page, the information-based measures. Okay. Actually, before we get started the information-based measures, we need to understand the information theory, which is already well developed and fundamental discipline with broad applications. So now we will, before we see the actual measures of the information for the proximity based on the information theory, we will define what is the information and how can we calculate the information. So here are examples for some similarity measures that based on the information theory, the mutual information in various versions. So the mutual information is one of the most famous similarity measure between two factors. And we will also see the maximal information coefficient. It is actually the continuous oops, continuous continuous version of mutual information by Binning. And the information-based measures usually can handle nonlinear relationship unlike the correlation. However, it is somewhat complicated and it takes some time to compute. So let's define the information here. So in the information theory, information relates to possible outcomes of an event. Okay, for example, we flip a coin. Okay, we flip a coin. Then there are two possible outcomes. The first outcome is head, and the second outcome is a tail. The possible outcome, possible result can be head or tail. The information means that information actually means this result. If we say someone to that the result of a flipping a coin is head, then it is the actual situation that we give the information to the other, and the other person who heard this one has the information or got the information. Okay. So the information is related to the result of this event. However, the amount of information, we need to define the amount of information is not the same. Okay, here, for example, if a coin has only two heads and no tails, then its outcome will be head, of course, because it only has two heads. It does not have any tail. So in this case, the outcome does not provide any information because everybody already knows the result will be head. Okay. And so here also we can think about, okay, here is a coin. It makes head with 99%, that it makes tail only with 1% probability, then we are more surprised when the result is tail than the result is head. So if somebody tells us, oh, the result of the coin toss was head, then we may not be that surprised because we can expect, oh, it's the 99% probability, so it's not that interesting or it's not that surprising. However, if somebody tells us that, oh, the result of this coin toss was tail, then we may be a lot surprised because the probability of tail is really small, really small. So we may be more surprised. So in we also we can be considered as we get more information than when we heard that the result of coin toss was head. So the amount of information is should be inversely related to the probability of an outcome. So here, the smaller the probability of an outcome, the more information it provides. Okay, and vice versa. The larger the probability of an outcome, the less information it provides. So here, and now the example of the first case, if the coin has two heads, it means that the coin for this coin, the probability of head is 100%, and the probability of tail is 0%. So in this case, the information, amount of information should be 0 because it does not give any information. So we define the information function as like this. Because the amount of information is inversely related to the probability of an outcome, let's say that just it is the amount of the information is 1 over pi. It is inversely related to the pi with the amount of information from the outcome I. However, if we put pi equals to 1, then we make it, we want to make the probability of the, we want to make the amount of information becomes 0. So here we take log here. Actually, okay, we take the log here. So this is defined by the amount of the information. Or we can say that it is minus log 1 over pi. Okay. So here I will write down amount of the information is minus log pi. Okay. Then in this page we will see the definition of entropy. The entropy is the expectation of the amount of information that this event gives. So if we flip a coin, we do not know the amount of information before the outcome has actually appeared. It means that if we toss a coin, then the result will be head or tail. If it is head, then we will get some amount of information related to the head. And if it is tail, also we get some amount of information which is related to the result of tail. However, we can calculate that the expected amount of information of this coin toss. Okay? So let's consider this coin toss is an event. Then we can make an expected value of this information from this event. So that is the definition of the entropy. So here, entropy for the event is usually written as Hx, and it is actually the expectation of the amount of the information from the result of the outcome of the x. Okay. So here we can, if the probabilities are probabilities of the outcomes of the x are discrete, it is from x1 to xn with the p1 to pn, then it can be written as summation pi, I is from 1 to the n, and amount of information of that x equals to xi, okay? Or in short, xi. And we know the amount of the information is minus log pi. So the entropy finally can be written as minus 1 I equals 1 to the n pi log pi. Okay. So the entropy can be considered as the expected information that we can get from the result of this event. Okay. And I wanna explain one more thing. The base of this log in the amount of information. I intentionally missed the base of this log. Here in computer science, traditionally we use the base of log as 2. Oops. 2. If we use 2 here, then the amount of information, the unit of this amount of information becomes a bit. However, we will use 2 usually because we are dealing with data analysis. However, if you see the entropy in the physics class, it is the natural entropy. So we use the natural log here. So the base of this log will be E, and this E, if we use E, the unit of this entropy will be net. However, we will use this one. And the value of entropy is between 0 and log 2n. It means that the minimum value of the entropy is 0 and the maximum value of the entropy is log n. So it has the minimum value 0 when one of the pj is 1 and other pi is 0 where I or I that is different from j. So in this case, hx will be okay here. For pj is 1 to the log 1. This one is 0. And for other i's, 0 multiplied by log 0. However, it is not, and there are many 0 multiplied by log 0. Actually, it has n minus 1 times, and this one will be 0. We know this one is 0. And for the 0 multiplied by log 0, we can get this value from taking limit epsilon to the 0, epsilon log epsilon. So in this case, we can get the, okay, 0, we can change the variables log 1 over epsilon, 1 over epsilon here like this, and it is, for example, other variable, let's say r goes to the infinity, log r over r, and using the L'Hopital's theorem, it's limit to r to the infinity. The derivative of log r is 1 over r, and this r, derivative of this r is 1, so it would be 0. Okay, so we can, if we take limit, we can also say here, oops, here should be minus here. Okay, these values will be 0 or zeros. So if we will get the minimum value of entropy if the probability of one outcome is 1 and the probability of other outcomes are 0. We can interpret it qualitatively also, because this case means that the outcome will be fixed only to one type of outcome J. So this event will not give any surprising result. So we will not get any information from this event because we already know before we see the result, we already know that the result will be outcome J. Okay. And this value of entropy has the maximal value of log n when all pi is 1 over n. it means that all probabilities of outcomes are the same, then we cannot expect the result at most. So we cannot guess the result when it is most difficult to guess the result when the all probability of the all results are the same. So in this case, if we calculate entropy, so minus summation 1 over n to the log 1 over n equals to I equals 1 to the n, so it will be minus log 1 over n, and it will be log n. Okay. So the entropy has minimum value 0 and maximum value log n. So here are example of the coin toss for the entropy. The probability of head is P and probability of tail is Q. So if P equals 1 or Q equals 1, then H would be 0, as we know. And if they are 1 over 2, then it has the maximum value, minus 1 over 2 log 1 over 2 minus 1 over 2 log 1 over 2 is minus log 1 over 2 equals to log 2 equals to 1. Okay. So it has the minimum value 0 and it has the maximum value 1. Okay. What is the entropy of a fair four-sided die? So it means that the outcome has P1 through P4 and all of the probability are 1 over 4. So if we calculate the entropy, minus 1 over 4 log 1 over 4, here log 2, minus 1 over 4 log 2 1 over 4 minus 1 over 4 log 2 1 over 4 minus 1 over 4 log 2 1 over 4. So it's log minus log 2 1 over 4, it's log 2 4 and it's 2. Okay. So here we can see that the entropy of fair four-sided die gives more information than a fair coin. Its expected information is larger than this one. Okay, we can easily think of that way. So the coin has two outcomes, head or tails. So if we get some information of the result of this coin toss, then we will get the result one of two. However, for the fair four-sided die, it has the value of 1, 2, 3, and 4. So because it has four possible outcomes. So the information of the result of four-sided die gives more information. The result of the four-sided die gives more information because there are four possible outcomes than the result of coin toss, which only has two possible outcomes. Okay. And if there are more cases, for example, 8-sided die, 16-sided die, then the amount of the expected information that we will get becomes larger and larger. Okay. And this is the entropy example of a sample data. For the hair color of the student, it is classified into 5 classes: black, brown, blonde, red, and other. And here are the counts. And if based on this count, we can make the probabilities here, and we can make the information of each class of hair color. I mean that the probability and the amount of the information. So if we sum all of these values, then we can get this value, and this is the entropy of the outcome of hair color. And the maximum case for this entropy, maximum case of this entropy for the hair color is 2.32. It is only the case when the probability of the all hair colors are the same, here 1/5. So for the data, we can get the entropy of some attribute if there are n different possible values or possible outcomes. Then we can count the number of each possible outcome as mi, and the total number of observation is m. Then pi can be approximated from the sample. It's mi over m. So this mi over m are put into the pi, so we can get the entropy from the sample. It is very easy to calculate it for discrete data. However, for the continuous data, this calculation may be harder. And now we will see the mutual information. Until now, we define the amount of the information and entropy, which is the very basic concept in the information theory. Now we will see the mutual information, which defines the similarity of two vectors, or two attributes, or two anything, two variables based on the information theory. Okay. The definition of mutual information, okay, conceptually, the definition of mutual information is that the information that one variable provides about another. So, for example, if there are two variables x and y, and let us say if we already knows know x, then what is the expected amount of information that we get when we know the result of y. Okay, and vice versa. The mutual information between x and y. Let's consider that we already know the information from x. Then, if we get the information of y, information we get we get the result of y, then how much of the information that we will get from this y when we already know x? We can define it in opposite way. If we when we already know the y, then what is the amount of the information newly given from the x? And the interesting point is that these two values are the same. So here, mutual information I, y is given as like this: h y minus h y given x, or h x minus h x given y. So here it means that this is the information from the result of y, and this is the information that information on y when we know x. Okay, so if x and y are somehow correlated, then the result of x can provide some information on y, and this is vice versa. And h y given x is defined as minus p x comma y I j p I j p x I comma y j log p y j given x y. Okay. So if we calculate this one, we can get this conditional entropy. We call this one as conditional entropy. So mutual information can be calculated in this both way, and another way to get the information, mutual information, is ix comma y is hx plus hy minus hx comma y. This is the joint entropy of x and y, and it is calculated like this: I j p xi comma yj. Oh, here's minus log p xi comma yj. Okay. So you can easily prove that this one and this one and this one, these three are all the same. I will not prove it. It is just remaining as homework. You don't need to submit. Okay. Please try to prove these three are all the same by yourself at home. And conceptually, this mutual information like this. This is the information from X. This is the information from Y. We don't consider this concept. I think this is not an appropriate example. However, we can calculate the mutual information in this way. So mutual information can compare the similarity of two vectors x and y. So it can be used as the similarity or dissimilarity measure for for our proximity measure. It can be considered as one of our proximity measures. Okay, and for the discrete variables, it is very easy to compute. However, the continuous variable, it is very difficult to calculate. So we will see how the case of the continuous variables in a few pages later. And the minimum value of this mutual information is 0 when x and y are independent. However, the maximum value of this mutual information is here log 2 minimum nx or ny. The maximum value of the entropy was log n. However, the maximum value of the mutual information is log 2 minimum of nx and ny. Here, nx and y are the number of possible outcomes of x and y. So here is the example how we can calculate the mutual information. First, we can calculate the here two variables x and y. The x is the student status, undergraduate, graduate, and y has three possible outcomes, grade A, B, and C. Here, okay, here. First, we can calculate the entropy of x, hx, like this, and here hy is like this, and we can make the joint cases. Undergrad A, undergrad B, undergrad C, grad A, grad B, grad C. And we can calculate the joint entropy. And we can calculate the mutual information like this. Sum of two entropies and minus joint entropy. And for the continuous variables, we usually make a beans for the variable so that we can make continuous variables into discrete categories. Okay, meaning is that if we have continuous variables and we can make some beans. So for example, we can bean the continuous variable into 5, 6, 7 discrete values. Okay. So if we use beaning both for the x and y, we can calculate the mutual information. However, this beaning, the result of the mutual information by this beaning, highly depending on how we make make a bean for continuous variables. So, okay, for maximum information coefficients here proposed in this paper, we okay, first the condition is of number of beans is nx multiplied by ny is less than n to the 0.6. Here, nx is the number of values of x and ny is number of values of y. These are number of beans. And n is the number of total observations. And calculated the mutual information and normalized by this one log to minimum of n x and then y. We know that this is the maximum value of these mutual information. So actually, so here we calculate I x comma y with meaning n x and ny over log 2 x and y. So we test a lot of many possible cases of nx and ny and meaning and and calculate this value and take the highest value of this value as the kind of the maximum information coefficient of the two continuous variables. And this is the last part of the similarity and dissimilarity part. If because there are so many attribute types, so in even for the one data object, there are sometimes here nominal attribute, ordinal attribute, interval attribute, ratio attribute. There are so many attributes, and for each types of attribute, the way to calculate similarity and dissimilarity can be different. However, so there are many cases that we need to combine these similarities. So there are many ways to calculate these similarity combinations. So here we will see a few ways to make some dissimilarity combinations. First of all, for the case attribute, we can calculate the similarity as kxy. If we can calculate the similarity, it can be easily changed into the similarity. And there are indicator variable delta k for the case attribute. If delta k is 0 when it has the 0 value on in the asymmetric attribute, or if one of the value has missing in the case attribute. Otherwise, the k equals to 1. Then the combination of the similarity of two vectors x and y is sum of delta k sk over sum of delta k. So here, for example, x has the sixth element and y has the sixth element. And we have similarities S1, S2, blah, 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 S6. However, the delta 1 and delta 2 and there are delta 6. However, if, for example, for example, S2 is the 0, 0 attribute of the symmetric attribute, then delta 2 will be 0 and if delta 3, if we miss the y3 value so that we cannot calculate S3 properly, then we put 0 here. So in this case, we can calculate the similarity as S1 plus S4 plus S5 as S6 and take the average of them. And it is actually 1 multiplied by S1 plus 0 multiplied by S2, 0 multiplied by S3, 1 multiplied by S4, 1 multiplied by S5, 1 multiplied by S6, and 1 plus 0 plus 0 plus 1 plus 1 plus 1. Okay? And this is actually the summation of delta K Sk over summation of delta K. Okay? So it is not the difficult one, it is just the concept of that we calculate the similarity for each attribute and choose which similarities we will use or not, and take the average of the used similarity. Okay. And if we want to, if we have some different importance of its similarity, we can give the weight. For example, if S1 is important, then S4, S5, S6, and we can put the W1 as 2 and W4 as 1, W5 as 1, for example, W6 as 0.5, for example. So then we can take the weighted average of the similarity, for example, 2 S1 plus 1 S4 plus 1 S5 plus 0.5 S6 as plus over 2 plus 1 plus 1 plus 0.5. Take the weighted average of this similarity. Okay? And it can be represented as 2, 1, S1 plus 1, 0, S2 plus 1, 0, S3, 1, 1, S4, 1, 1, S5, 1, 0.5, S6, and 2, 1 plus 1, 0 plus 1, 0 plus 1, 1 plus 1, 1 plus 1, 0.5. It is also just summation of WK delta K. And here the numerator is summation of WK delta K SK. Okay, the weighted average of the previous version. Also, we can define a weight form of distance. We can put different weight for each attribute of the data points when we calculate the distance. Actually, okay, the distance here. Okay. So that's the end of this class. Then in the next class, we will finish, maybe we can finish the chapter 1 in the next class, which the remaining part is data pre-processing part. Okay, so please review today's content at your home, and let's see you on the next class.